Did I send you any? Wait. Did I send you any? Is that all like? Where's that? Oh, I didn't say.
I'm really right in good to you. Way too close for comfort. Yeah.
Oh yeah.
For sure. He's what? Yeah, I got your.
Oh, so that works.
Now there's H.
Where were you in?
Why?
That's not real. But it wasn't even.
So
So that's weird.
Well, I can't even
there he is. This
Yeah,
Wait, what is your group chat?
That was.
You have to be in, currently be in Spanish.
You don't go
I
with
think. I have no idea. I'm not taking April. Yeah. Wait, no, you're a junior. Yeah. Did you? So I guess you took it in 8th grade. Yeah, I guess that.
Good morning, FHS. Today is Thursday, February 8th, 2024. Would you please join me in a minute of silence?
Didn't it block?
Please stand if you are able and join me in the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Thank you and have a great day.
Alright, good morning guys. You might want to make sure that you got the 85 and 89 in. The two things I asked you guys to turn in last class or for homework if you didn't turn them in during class. I want to start grading those in just a minute, so if you don't have those in a minute, then those will be late. But we are going to look at some integration notes, specifically logarithmic integration notes. So with that, there's not actually anything new that I'll be saying to you, but I feel like that needs more practice. Then I gave you number 88 last class, which was the test review, and we did FRQ 1. I'd like us to do FRQ 2, and then question number 8 on the back. I think that's good practice, and you get a little bit of your test review done that way. So 2 things at once. And then we'll finish up class with the circuits you picked up, which should be 91. Same thing, velocity, distance, displacement, acceleration, stuff that I think we need more practice on, but not anything that is completely new. So, again, nothing new today, but just trying to get a little bit extra practice and a little bit more focus on the stuff that I know would be beneficial. Actually, I take that back. There is one new thing on this first handout, but it's at the very end, and it's not as important. It's just not very common, but that's fine. Okay, so we're going to talk about some integration here, and again, it's nothing different, but we're going to focus on when you need to do logarithmic integration. So the thing that you need to have memorized here is that when you want to integrate 1 over x, that's the natural log of the absolute value of x. And then maybe plus c, depending on the type of integration that it is. So, I know you've heard that one before, but questions 1 and 2 here, these are about as easy as that question type would be. If you have a constant, like 5, you're welcome to pull it out front. Deal with it after the calculus, just like we did with derivatives. So the answer to this would be 5 natural log absolute value of x plus c. And then same idea with question 2. I've got 1 over something, so sometimes that means natural log, sometimes it doesn't. Typically, you want to just go ahead and try natural log, and if there's no chain rule along with that, then you shouldn't need to use substitution for that. So again, in the back of your mind, you should always be checking with derivatives. The derivative of this would be this, and the derivative of this would be this. Same thing that I started with. It's good for you to continue to practice those as well. Not as important today, question 3, but there's a couple questions you'll see tomorrow like this one, where as much as you may want to do use substitution there, as much as you may realize it's probably got something to do with natural logs, because that's what this worksheet is titled, sometimes you have to do a little bit of rearranging here. Same thing with derivatives. If there's some algebra you can do, some exponents you could do, some fraction stuff that you can do, typically you want to try to do that right away if possible. So for this guy, I would suggest splitting apart your fraction. You can split apart numerators, not denominators. And then if you simplify this with exponent rules, this would just be undoing the power rule. This is natural log integration. So not too terribly difficult, but if you don't consider rewriting fractions, rewriting exponents, rewriting with some sort of algebra before you deal with the calculus and the antiderivative, sometimes you're just not going to be able to work some questions. Okay, most of the rest of these questions on this side here will require use substitution. So if you don't understand why number 4 needs use substitution, if you think this is very similar to question 2, again, it's fine to go ahead and do this. If I want 1 over 2x plus 5, I could try this, but why? How should I know that this isn't the correct answer? One more time? I just can't hear you. Right, so when you take the derivative of this, you get the 1 over 2x plus 5, but because of chain rule, it's also going to multiply by 2. So sometimes, if it's just one step of chain rule like that, if I know it's going to create a 2 that I don't want, I could throw a 1/2 out front, and that's going to balance it out. If you don't want to do that, if you don't want to try to keep up with that, undoing that stuff in your head, that's where it's probably simpler to just go ahead and jump into the use substitution process. 2. And instead of 1 over 2x plus 5, I could say 1 over u. And instead of saying 1 dx, I could put du. And now it looks like what we wrote on the top of our paper. It's the one that we basically have to have memorized here. So natural log, absolute value of whatever u was. Oh, I did forget one thing, didn't I? Here I divided by 2, so here I should have divided by 2. So again, I could kind of see that why that 1/2 needed to be there. So feel free to practice that sometimes. Again, one step of chain rule is not too hard to undo in your head, but also if you're familiar with the U substitution process, and we're going to practice it even more tomorrow, today I'm basically doing all the U substitution for you in these notes. But if you know that process, like, yeah, it's going to take you an extra 60 seconds, but at least you know what's going to be done. Okay, so question 5. Again, I can't split this fraction up because you can split apart numerators, not denominators. So even if you aren't sure if it's U substitution, again, in about the time that I can say that, and then I look at what I have, I'm already convinced that U substitution should be just fine. This is like 1 over u, and this stuff is equal to 1/2 du. So from the first 5 questions here, I think you should start to see that if you've got a lot of stuff in a denominator, it's not guaranteed to be true, but it more than likely, if there's some stuff in the denominator, it could be some sort of natural log integration. And again, if you know the U substitution process, you should be able to write it in a way that just matches the thing we memorized. Okay, question 6 is a little bit even more obvious to me, just glancing at it, because I can guess that if I had picked my denominator to be u, du looks like the rest of the stuff. So it doesn't take me long to figure out that that is doesn't take very long for me to realize that U substitution is going to work out here. So this ends up being 1 over u. All of this stuff is equal to du. So if you have that one memorized, 1 over u integrates as natural log of absolute value of u, and then put the plus c if it's indefinite. Almost the same question on number 7. If you don't know what to pick out as u, again, one of the few things I hope you get out of this little bit of practice here is if you don't know what to pick out as u, might be a good idea to try the denominator. And if we do that in this question, unfortunately, this doesn't look like the other parts here. The denominator could be written as 1 over u, but I need the rest of this stuff to be x squared plus 2x plus 3 and a dx. So is there any way to change this to this? Right, so we're lucky that this needs to be divided by 3 and this and this. So divide all of the left side by 3. It's the same as dividing the whole left side by 3. Left and right by 3. So it may not be obvious that it's a perfect fit, but if you write down what you have versus what you need, again, I think it's a little bit easier for you to see. And with that, you're left behind the thing that you need to memorize anyway. I did put this natural log thing in your first notes, but I know you don't practice it a lot. So u is in the denominator, so good chance when you integrate it should be some sort of natural log integration. Bless you. Okay, let's look at a couple more, and then we can flip over and look at a couple other cases here. So, I think in question 8, it would be a bad idea to pick the denominator as u, so you can't just say that all the time. But since this natural log is stuck in the square, we could maybe try that as u. And that looks good, because 1 over x dx, I have that in here. So this is really like u squared du. So I guess this one isn't really logarithmic integration, but we picked out u to be the natural log piece. But undo the power rule, plug your u back in. And on a high stakes question, quiz or test, if you had time, try to check it by taking the derivative. Just make sure you don't forget the chain rule, because that's probably what's going to make or break you. If you check it by taking the derivative and don't consider chain rule, there's a good chance you'll miss it. Alright, question 9 has a little bit of a typo here. This is supposed to be sine of t. So again, if you're not sure what u should be, I'm not saying it works 100% of the time, but if you're not sure, maybe pick out u to be your denominator. Five seconds later, you should have a good hint if you're on the right track. I needed cosine t dt, and I have cosine t dt. So I don't even have to do anything else here. This is like 1 over u du, which integrates as a natural log absolute value u plus c. Hopefully you're kind of seeing the pattern between all these questions. Pretty much the same idea. And if you're very comfortable with this integration, it makes the end of the question very quick. I had asked you guys, without going over any of these questions, which of this to pick. I think I'd get a lot of different answers for you. But again, sometimes if you're not sure, you just got to pick something and run with it. Now, I will say, based on some conversations I've had with you guys, it seems like maybe the trig derivatives are something you have forgotten because you don't get to use them as much. On a test, remember you could rewrite it with trig functions. Those of you that did trig last year should know that by heart, because you had to do it 300 times, if not more. But then you could take the derivative of this with the quotient rule. Of course, that's a pain, but you could at least figure it out if it ended up being on the test. But the derivative of secant is secant tangent, which is exactly what I needed. So now I know I'm on the right track. And when I rewrite it, it's going to work out with natural logs, since I was trying to undo a 1 over u. Okay, on the back we're going to look at 2 kind of special case type of questions. I just want you to be exposed to those in case you ever see them, and then that way you have an idea of how you can maybe start them, if nothing else. But is there anything you guys would like to clear up about the front page? Anything 1 through 10 that's not making sense? Again, this shouldn't be new. I'm just kind of like throwing some more exposure at you. To more repetition should make it a little bit easier. But okay, well, on questions 11 and 12, I would say these are a little bit harder to try to figure out what u should be. And if you just instantly start off with u substitution, there's nothing that you're going to pick that's going to work. Same with 11 and 12. Also, it doesn't look like it has anything to do with natural log integration. But if you remember question 2 on the front page, I said sometimes you should do some algebra or some fractions or some exponents, or I guess even rarer, but sometimes trig identities. So cotangent is the same thing as cosine over sine. And if you, well, first off, you have to know that identity. That one's just too important. You don't have your name on this, so I'm not going to know who this goes to. Also, I need that at the start of class or in Google Classroom. I'm not stopping class.
I'm just having trouble finding it. Thank you.
Please organize your binder then. Okay, if you think to write cotangent as cosine over sine, now you can see something in the denominator like we did on the front page. So you may try to pick the denominator to be something, take the derivative, make sure that you think about chain rule when you've taken the derivative. Also, I know it's tempting to do du over dx because x is what we usually do, but this is d theta. It doesn't really change much of the question, but looks like I need to multiply both sides by 3 so that I can get it to be a cosine theta over 3 d theta. So this is like 1 over u du if I put a 3 out front. So again, it didn't look like u substitution would help. It didn't look like this had anything to do with logarithmic integration. So near the bottom of your list, sometimes if you can't think of anything else to try, maybe try one of these quotient identities like this. And then go ahead and integrate and plug u back in. I'm going to do the same trick for 12, but not the same trig identity. Cotangent is cosine over sine, whereas tangent would be sine over cosine. Again, and this would not be my first thought here. I would first try to think of stuff that's easier. I would first try u substitution, but anything you pick for u is not going to work. So eventually, when you're out of other ideas, maybe consider changing tangent into sine over cosine. Now you've got a denominator that might be a good candidate for u. Now be careful on this part because there's chain rule twice. The derivative of cosine something is negative sine something times the derivative of the inside. The derivative of e to something is e to something. And there's an inside of that. Chain rule 2 times. And of course, if you blaze past that, then you're going to be confused and not be able to figure that one out. So looks like the negatives cancel out. I've got this stuff, which is, also I have a dx. This matches up with all of that. So even though it's looking kind of crazy, really I end up with 1 over u, and all of this other mess ended up being du. If you do the chain rule correctly, everything else was there that you needed. So then the calculus part, well, I guess this is, derivative part is calculus too, but the antiderivative part would just be natural log absolute value of u plus c. Again, if you want to check that one with the derivative, then go for it, but you would have to do chain rule 3 times, I think, to make sure. All of this is the inside, then this is the inside, then this is the inside. There's 3 chain rules there if you're checking that one. Okay, I'll be honest that I don't see this question very often, this question type. That doesn't mean that we couldn't put this question type on your test, but I would be surprised if you had one like that on the AP exam. Yeah.
Did the -1 come from the Okay.
Yeah. The derivative of e to the x would just be e to the x, but e to the negative x would be e to the negative x times the derivative of the inside. So that was the second chain rule step.
Thank you.
Yeah, as I said, that's easy to overlook if we're not being careful. Okay, so along the same lines, I have seen questions like 13, 14, and 15 on your AP exam, but they don't ask it every year. So unfortunately, this will probably be the one time I tell you, and you just have to kind of tuck it away in your brain. And maybe if it showed up again this year and nothing else was working and you had time to dig around at it and you finished everything else, maybe you could come back to these. But these questions, we are going to need to recall how to do long division. Now again, I'm skipping past the part where I would try everything else that's easier first. Try use substitution, it's not going to work. Think about trig identities like the last two questions, but there's no trig identities. I can't just split apart my fraction. Well, actually you can maybe split apart your fraction. That might work, but that would be pretty tough. Rarely they will ask you to do long division here. So if I try to do x plus 1 divided into this stuff, now, if you don't remember long division, you need to give me your full attention here because I'm not going to spend 20 minutes on it. But you got to think about the thing times x that gives you x squared, and then also multiply it by 1. And then you need to subtract all of this stuff. So change the signs and add. Do it again. Negative 4, because negative 4 times x gives you negative 4x. Also times 1, change the signs and add. And when you did this in Algebra 2, and we reviewed this in pre-calculus, when you do this long division, what I'm able to do is rewrite this question. Instead of saying this divided by this stuff divided by this ends up being the quotient, which is x minus 4, plus the remainder over the divisor. So long division, I'm really just making this look different. Instead of it looking like this, I'm making it look like that. The reason why this is so much better is I can do this in my head. I can do this one term at a time now. Undo power rule, undo power rule, and this is a logarithmic integration that doesn't have chain rule. So, I'm sure there's not a lot of long division fans in here, but you have to appreciate that it went from being a question that we really just didn't have any tools for to rewriting it in a way that the antiderivative took about 10 seconds. So let's look at that 2 more times. And again, just file that away as, you know, when nothing else works and you have time, you can always kind of backtrack to that as a last resort. Okay, so again, I'm not trying to give you like any special hints that this is going to be important or anything, but after you try everything else, no algebra works, no trig identities, no u substitution, nothing you pick for u is going to work, then you might consider, well, what would it look like if I did long division? I could rewrite the question and it may look in a way that's much easier. So we would end up with x squared, because x squared times x is what gives you x cubed. Also x squared times negative 3. We really want to subtract all of this, so I always tell my pre-cal students to just change the signs and add. That tends to be less problematic. And I end up with a quotient of x squared and a remainder of 5. So this divided into this gives me x squared plus, so quotient plus remainder over divisor. And now that I've done the long division part, the integration is going to be pretty easy here. Undo power rule. This is 5 times 1 over x plus x minus 3, which could be natural log. Since that doesn't have a chain rule piece to it, the derivative of x minus 3 is just 1, I don't have to do u substitution there. Okay, I do want to give you a chance here to just quickly try to see if that really is sinking in for you. So if you would, go ahead and try the long division part of 15, and I'll give you a minute or two to do that. And then that way you'll know if you do remember long division correctly or not, or if that's something you might want to look over again in your free time. So just a couple minutes. You don't have to do the whole thing, just try to do the long division. Okay, let's see how you did with the long division. So, first part should have been x squared, because x squared times x squared is what gives you x to the 4th. You also need to multiply it by 2, which gives you 2x squared. And my advice would be change both signs and then try to add. So x to the 4th minus x to the 4th goes to 0. These are not like terms. You cannot force them together. I've got this many x squareds, this many x's, and this as a constant. You can't force these together. Can't combine like terms if they're not like terms. The next part of your long division should be negative 2, because negative 2 times x squared is what gives us negative 2x squared. Also need to multiply it by 2 to get negative 4. You don't have to line it up here, but most people do. Change the signs and add. It looks like if you did the long division correctly, this is the same thing as x squared minus 2 plus the remainder over the divisor. So to finish, again, I didn't ask you to do this part, but to finish this integration, part of this should be pretty easy. Undo power rule. Undo power rule. And then unfortunately for this part, this isn't just undoing power rule. It doesn't match anything else we've learned. Unfortunately for this, I would have to kind of sidebar here and try use substitution. It looks like this would be 1 over u du. So final answer, 1/3 x cubed minus 2x plus the natural log of the absolute value of what I was calling u. Anything else?
Should we put a 1/2 in front of the natural log? Because
Oh.
you should use the 1/2.
Yeah, I'm sorry. I wrote it down and I didn't do it over here. So, okay, there was one mistake I had. Plus C. You get so worked up in the question that forgetting C is really common. Also, I want to kind of say this just because mathematically this bugs me a little bit, but way back, and I'll zoom back out and make sure you guys don't have questions. But really, when I integrated way up here, there could have been a constant that I didn't see, So simply ignoring the plus C for a while and then remembering it is not really good enough. I really should have had a plus C here, and then you can put it plus here. It's not the same constant necessarily, but once you integrate, you should have a plus C. Just because I didn't integrate everything doesn't mean that there's not a plus C. There could have been a plus C from this part of the integration. Okay, so again, not that common. This is not a question that they ask every year on your AP exam, so unfortunately it's probably not something we will even look at again this year, because we will focus on the stuff that is a little bit more predictable to be on your AP exam, but I needed you to know that that's a possibility. So, is there anything about 15 you want to clarify before we move on? Okay. Then number that guy as number 90 for your binder. And then the next piece that I'd like to do with you is number 88, your test review I gave to you early last class. And we did FRQ 1. I'd like to do FRQ 2 today. And I would like to do one question on the back. So find that in your binder, please.
Do you have any more copies of 88?
Let me check on the bottom of the bookshelf.
Okay.
It's we're on the website. It's just a single page. Or Thompson, they may just be in the box over there, I'm not sure. I tried to put some in the box, but see if there's an 88 in that tab over there. Okay, so we looked at FRQ 1 last time, and it was a calculator FRQ. We're going to look at FRQ 2 this time. It's also a calculator FRQ. So keep in mind there might be some stuff that's easier to do with the calculator. And this one only has 3 parts. We'll do FRQ 3 tomorrow too, so you don't need to. This is a B week, so I see you again tomorrow. Alright, but as you guys finish getting that sorted out here, question 2 says, a particle moves along the x-axis. So, x-axis, there's a particle that's moving back and forth, left and right. The time is between 0 and 16, and we're told what the velocity is. E to the 2 sine t minus 1. Okay, part A wants us to think about when is the particle moving to the left. So, like we did with FRQ1, I'm not giving you time to work it out, but I do want you to spend 20 seconds thinking about what you think the process should be. What would you start off trying to do to see if you understand what they're asking. So how are we supposed to know when the particle goes to the left?
You integrate the values of 0 to 16.
If you integrate from 0 to 16, that would be the same as the change in position over the 16 hours or 16 minutes or whatever it is. Oh, yeah, sorry, I was just letting y'all think about it for a second. Something's going to the left when, but the velocity is negative. When velocity is positive, it goes to the right. When velocity is negative, it goes to the left. So, how can I try to figure out when this stuff is less than 1? Alright, you have a calculator. You can graph it. You can change the window settings. Your calculator would need to be in radian mode because there's a trig function here, but for us it should always be in radian mode. So you could do that, and, well, I don't know, let's just go ahead and do it. Oh, okay, I've already got it here for my 8A class. So here's what the velocity function looks like. Personally, I would change the window settings from 0 to 16 because that's all this question cares about anyway. And the particles going to the left when velocity is negative. So I can kind of see when it's negative. So I need to figure out when it starts being negative and ends being negative. So we practiced this last semester. You could do second trace, calculate a 0, move your cursor to the left of the 0 you're trying to find before you hit enter on left bound. Move your cursor to the right of the 0 you're trying to find before you hit enter on right bound. Hit enter to skip guess, and your calculator will bounce that point back and forth until it gets as close to y equals 0 as it can. So he looks like he starts having a negative velocity at 3.142. Remember, we always round to 3 decimal places. But doesn't that sound kind of familiar?
That is pi right there.
Right, so you can do 3 decimal places, that's fine, but also you might recognize that it's pi. Okay, and then he stops here, so same steps. Trace a 0, enter to the left, enter to the right, enter to skip guess. Looks like it stops at 6.283. Does that sound familiar? 2 pi. So again, the AP exam is perfectly happy with 3 decimal places. Never 2, never 4, never 5, never 8, 3 decimal places. But if you recognize that as 2 pi, you could say 2 pi. Okay, and looks like velocity was negative over here as well. Now, I can do the second trace and do that 2 more times, but just based on like how the period of this function and how it's repeating, what would you guess this to be? Okay, so if you do trace 3 pi enter, your calculator jumps to that point and your guess was correct. So it's probably 3 pi to
4 pi.
Okay, so trace 4 pi to jump to that, and you're correct. 3 pi to 4 pi. 3 pi to 4 pi. Okay, is that it? Good. Got to be careful here. It's negative right here too. So I'm going to guess that it starts at 5 pi to confirm. Trace 5 pi enter. Sure enough, that's when it starts being negative again. And so should I say 5 pi to 6 pi maybe? Right, this question only cares about the 16. So 5 pi to 16. So honestly, the calculator is doing almost everything for you there. You have to remember, if this is a calculator FRQ, maybe you could do that by hand. It's entirely possible. I don't think it would be the hardest thing that you guys have ever had to do. But if you have a calculator, why even risk it? This would be your justification. All of that would be your answer. You have an issue? What's the problem? Oh. Okay, I was trying to find the scoring guide that goes with that, and I don't see it in my notes here. So my guess would be there'd probably be 1 point for the justification and 1 to 2 or 3 points for the answer, since there's multiple parts. Oh. Okay, second part of this FRQ. Wants you to think about what's the total distance traveled. So we have velocity and we want the total distance. So once again, 10 seconds to yourself. Think about what you think the process should be and see if it ends up being the same thing that I said. Okay, so if you integrate, this isn't about this question, but if you integrate acceleration, it gives you the change in the function below it. Integrating acceleration would give you the change in velocity. So for us, we want to know how the distance is changing. So we would integrate the velocity. That gives us the change in position. And I want to do it from 0 to 4. But since it says total distance, this is where we needed to always throw in those absolute value signs. Because what's going to happen here is if this thing goes to the right, if you don't have the absolute value signs, going to the right is going to add to the total distance. But then if it just goes back to where it started, it's going to think the total distance is 0. Because without the absolute value sign, it's really doing displacement, not distance. So whether it's going right, positive, or left, negative, we wanted to add to the total values. So that needs to be on your paper. That would probably, there's a good chance that would be worth a point or 2. And calculator does the rest of it as long as you're in radian mode. My calculator's thinking this is not the easiest calculation for it, but 524. And of course we should probably say miles or feet or centimeters or whatever the units are. I think this is probably just a made up question, but we could at least say units, singular, not squared because it's not area, not cube because it's not volume. Okay, I feel like you guys have been doing pretty good with the absolute value on total distance. And again, that's just real common, so you're going to see that another dozen times this semester. Okay, last part I want you to think about, and then we will answer. And then I will highly suggest that you guys put a star by any of those that you feel like you couldn't have done before today, so because that would be exactly what you need to study. Okay, part C. Is there any time between 0 and 16 that the particle returns to the origin? Okay, well first off, I don't remember it starting at the origin, but if I reread the question here, they did tell me that it starts at the origin. Okay, so think about what you think the process should be to do that, and then we'll do it on the board. How would you go about figuring out if it ever returns back to the origin? Okay, well, what we could do is we could graph the position function in our calculator, and then we could see when it was back at 0, but we don't have the position equation. We could find it by integrating. I don't know how tough that's going to be for my calculator, but the position would be where it starts at. I said it starts at the origin. And then how it changes over time is integration. So, I don't know, I could try 0 to t. I don't want to do 16 because then it's only going to think about time 16. It might be back at 0 another time of this function. Integrating velocity gives you position. It's just, I'm hesitating here because I know when you try to get your calculator to graph an integral, that calculation is kind of tough for it, and sometimes it is super slow. So let's see if the calculator can handle it. Okay, so here's function. I kind of want you to see it trying to graph it, because even if this does work, I want you to see it's kind of painful. Okay, that's not too bad. Sometimes it's a lot slower than that. But you have to realize, as it gets to like x equals 3, it's having to add up all the values before it. And then when it gets to x 3.1, it has to add all the values up before it. Okay, so yeah, it's slowing down a bit now. I guess one thing you could do to still survive on this question is you could start working on another question and let your calculator keep doing this.
Looks like.
Sorry?
I'll give you the answer.
Yeah, but how do you know it's not going to come back down here?
Because it's a repeating graph of the velocity graph. So it's going to continue like this. The
Okay.
area above the graph velocity is greater than the area below the graph.
Okay, now that's a better way to think of it. So my calculator's still thinking here, and I do think it goes up forever. So based on this graph, if you trust me that it goes up forever, when does it return to the origin? It doesn't. We're at the origin here, and then the position just gets bigger and bigger, smaller a little bit, and then bigger and bigger, and then smaller a little bit. So the other thing we could do, and this is what I did in my A-Day classes. If I can get my calculator to quit. Again, trying to graph an integral, sometimes you can make it work, but it's pretty rough. The other thing we could do is we could graph velocity. And I had this up earlier, so I guess I could have used it. Okay, so there's velocity. What about this velocity graph tells me how the position is changing?
It's above the x-axis. The position is increasing.
Okay, that's true. I guess what I'm trying to lean back to versus what I first graphed, I was trying to graph the integral of velocity. What's a way to sometimes see integration on a graph though? Area. So the area under a velocity graph is the same as the change in position. So right here, I'm at the origin, and then all this area shows me how the position is going to the right, and then all this area is showing me how it's going to the left, because it's negative. So it goes right a bunch, left a little bit, and that's what we started to see on the last graph. And then it goes right a bunch, left a little bit, right a bunch, left a tiny bit. So again, sometimes you can think of that as an integral, sometimes you need to think of that as area under a curve. So the quick answer is, does it ever return to the origin? No. And I think you could probably say this a couple different ways. But what I would probably go with is now I already have the position function here. So the position function is always greater than 0 after t equals 0. I'd probably try to say something like that. It just got further away. What I would expect you guys to say is that sometimes is maybe not the best approach, but you might say the graph does this. The problem when you say that is nobody can assume what graph you're talking about. Nobody can assume what the x-axis means. Nobody can assume if you talk about area of the graph, you have to describe all of those things if you're going to go that route. So you could say graphing the velocity function, the area above the curve increases quicker than the area under the curve above the x-axis increases faster than the area under the curve below the x-axis. So you could go something like that, but you just don't just say the graph, the x-axis. You got to be specific. So, but I think that's a good one for you guys to see with the calculator, because this calculator does not love graphing integrals. It's very strenuous on those calculators. So your phones would be much better calculators than the calculators we use for processing power. Okay, so again, if I was you, pick one or two of those parts that you think that was not intuitive to you, put a star by those, and look back at them in case they show up on your next FRQ. Last thing I'd like to do with you guys before I let you work on the circuit at your pace, on the back, I'm asking you to do this one question today. Not that there's anything really special about this question, but it's one more done for your test review. And if you struggle with this one, that would be a red flag that you need to start putting in some time. So go ahead and do that one. We'll look it over, and then I'll remind you the binder numbers and what else you need to try to get accomplished with the rest of class. Okay, so this one was a U substitution question. Now those of you that did not take pre-cal, this is one of the small little things that just becomes intuitive to everybody else. This is not cosine times x to the fifth, it's cosine of x to the fifth. So the x to the fifth is the thing that's trapped inside something, which is, of course, your hint that it might be your u. du was 5x to the fourth dx. I need 1x to the fourth dx. Divide this side by 5. Divide this side by 5. And rewrite. This is cosine u. The rest of it is du. And what can we take the derivative of to get cosine of something? Sine or negative sine? It's just sine. Plug u back in, and feel free to check with derivative. That's an easy one to check with derivatives. Oh, and if I actually had checked it, I would have seen I messed up. Yeah, you need the 1/5. Derivative of sine something is cosine something times the chain rule would create a 5x to the fourth. Multiply it by my 1/5 to get 1x to the fourth. So I think I made this mistake twice today though, or maybe 3 times. I wrote it down here and I didn't do a good job of putting it over here. So hopefully you guys don't have that same problem. But at the same time, I would check all of my stuff by taking the derivative, so I usually catch it before I move on. Okay, y'all wanna, is there something about 8 you wanna ask? Again, if you feel like that one's tough, then you need to start maybe re-practicing some of that use substitution stuff. Use substitution will be the biggest part of your next assessment. Okay, to finish up class today, you guys have about almost 45 minutes here, but I would like you to try the circuit. It's not a long one. It doesn't have anything new. A little bit about velocity, distance, displacement, acceleration. Of course, 1 or 2 of them can be a little trickier, but you also have got 40 minutes. So make sure you have that done. And I would suggest that you also continue on with your test review. Of course, you're going to have to do that at some point anyway, so the sooner you start chipping away at it, the more time you will have to study if you need it. Okay, and then that should finish up class for today. Of course, if your table gets stuck on any of these circuit questions, please let me know and let me help. Just because you've seen this stuff before doesn't mean that they're all easy questions. And as the directions say, there are a few of these that you're welcome to use the calculator on, but make sure that you're writing down like what you're putting in the calculator or what you're seeing from what graph to help you with that.